Good afternoon, everyone, and welcome to our annual Hans Liebe lectureship. I always use this picture of Hans working in his laboratory to motivate our lectureship, our lecture for the day. You can see him working behind his apparatus. That apparatus was used to develop measurements that went into the absorption models that we use today. Many of us use them even on a daily basis. The Hans Liebe lectureship is hosted by the U.S. National Committee of URSI with the generous support of the Liebe family, and it established the Hans Liebe lectureship in microwave and optical spectroscopy as applied to radio science, Earth remote sensing, radio astronomy, and telecommunications. These are disciplines that underpin a lot of what we do in URSI. The lectureship provides travel support and an honorarium for a distinguished member of the radio science community to deliver a lecture on the professional topic of their interest at each of the annual USNC-URSI radio science meetings. Hans would be very proud, I'm sure, to see the legacy of what his propagation model has left behind, because we use it in so many areas in all of those disciplines that I just mentioned. Let's see if we can find the right arrow key. Oh, there we go. Our 11th Hans Liebe Fellow is Professor Ulrich Lohnert, Professor for Meteorology at the University of Cologne in Cologne, Germany. He is Professor of Meteorology since 2020 leads the research group called Exploiting Observations in Meteorology. Before becoming an extraordinary professor in 2020, it's a title provided to professors of a particular experience, he co-led the research group on integrated ground-based remote sensing since 2007. And in 2012, he obtained his habilitation in meteorology from the University of Cologne following a time as assistant professor at the Meteorological Institute. This is the Ludwig Maximilians University in Munich, and he was at that 2004 to 2006. His research interests are in using ground-based remote sensing for enhanced atmospheric process understanding and improving numerical weather models. He has been coordinator of German research network projects funded by the German Ministry for Research and Education, the BMBF, and he has acted as PI in numerous nationally funded projects with the German Research Foundation, or DFG, and BMBF. He has established research projects with the German Weather Service, the DWD, as well, and since 2020, he is PI within the Actress D initiative that I'm sure he'll talk about. He's also co-chair of a World Meteorological Organization working group on data assimilation and observation systems, and has been working as a group leader on numerous European Union-funded projects. Professor Lohnert's lecture today will be on ground-based microwave radiometers, missing puzzle pieces in laying the picture of the atmospheric state. And with that, Professor Lohnert.
Thank you very much for the introduction. So just...
Yep. Shall I leave this for you?
Yeah, that's good. Thank you. Okay. The
cell phone. All right,
Okay,
try that. And maybe try to keep the antenna outside the pocket.
antenna is this one.
Yeah.
Yeah. Okay, I'll try it this way. Thank you very much for the introduction, Al, and good afternoon to all of you. First of all, I'm very honored to be able to present some of my current research here in the Hans Liebe lectureship. I'm very excited to do that, and yeah, I think it's a great honor to be able to step into the footsteps of some of the achievements that Hans Liebe has achieved for the meteorological community. So you've already mentioned my title today, Al. Just a few pictures. This is something about my background. So I've been dealing with ground-based microwave radiometers all my scientific career in different sizes, different configurations under different challenging conditions. And these systems have accompanied me, and they have mounted into the JOICE Observatory, which my group and I are operating at the research center in Jülich, which is in the western part of Germany, close to the city of Cologne. And we are cooperating strongly at the university with the research center and with the University of Bonn, which is just about 30 kilometers away from Cologne. And we are operating an array of not only passive microwave radiometer instruments, but active microwave radars for cloud remote sensing and many properties of the boundary layer. So JOICE stands for Jülich Observatory for Cloud Evolution, and with these mainly ground-based remote sensing observations, we are looking into the science in the cloud life cycle. We are testing new instruments and developing new instruments with the manufacturers together. We are developing inverse methods, so retrievals for deriving mostly the atmospheric boundary layer thermodynamic state. We are evaluating models. We are performing data simulation trials with these observations, but we're also part of infrastructures that are dealing with the standardization and the dissemination of the data. And of course, we also use this observatory for teaching. So our bachelor students, master students, and PhD students are actively working with these data, and we organize summer schools and excursions to the stations, etc. And we are part of the ACTRIS, the Aerosol Cloud and Trace Gases Research Infrastructure, funded by the European Union, which I will say a little bit more about later. I mentioned my working group. I'm basically the manager, and the research is done by my postdocs and PhDs. Just some of them were the pictures you can see here. We cooperate with quite a number of institutions, with the German Weather Service, for example, but also with the ECMWF, and for example, also with ESA, because we use our observations for satellite CalVal. Okay, that's enough in the own issues. Coming to the observations. So the observation components of the global observing system as defined by the WMO, so by the World Meteorology Organization, are made up of different parts sketched on this picture here. So surface observations, classical synop stations, upper air measurements, so radiosondes, or aircraft-based profiling at large airport hubs. Satellites are probably the most important part for numerical weather prediction. Marine observations on buoys, weather radar, ... Concerning ground-based profilers, so what we do at JOICE and what my research group is looking into, there is a statement actually, if you go to this official website of WMO, that states that ground-based profilers do have a great potential to be a valuable part of integrated networks. So that's more going into the future of the global observation system. So what is actually the status of atmospheric profiling of winds, temperature, and water vapor? Well, we all know that radiosondes are a basis, so, but they have the problem of horizontal and temporal coverage. We cannot cover the diurnal cycle with just 1 or 2 radiosonde ascents, and mesoscale circulations are also not resolvable, for example. So there's an observation gap here that is required to be filled. Then we have aircraft data. So for example, from the AMDAR, EMDAR, or MODES reports, which are regionally limited to large airports and do not provide standardized humidity observations yet. Then we have, of course, the polar orbiting satellites, for example, with the well-known AMZU A and B sensors, but also the highly resolving infrared spectrometer measurements from AIRS or YASI. But typical, there's only 2 times daily overpasses over any arbitrary location worldwide. And one other thing is that the atmospheric boundary layer is not well resolved at all. So this is due to variable surface emissivity and the low vertical resolution of these sensors, especially in the area of the surface. So what to do? We need to somehow fill these gaps, and this could be done by ground-based profilers, right? And also, the WMO rolling review of requirements states that there is this strong observation gap of winds, temperature, and humidity in the boundary layer concerning temporal and horizontal resolution. The question is how we can fill them, and the question is if ground-based profilers can lead to filling this observational gap in the future. So this is what I want to talk to you about in this lecture. So especially about filling the gap with ground-based microwave radiometers. I want to introduce you to the benefits, their limitations, what networks are currently evolving, and what the first data simulation impacts into numerical weather prediction models of these observations are. And then completing the puzzle through synergy with other ground-based remote sensors. So how good do we get if we don't use only a ground-based microwave radiometer? And maybe even to combine these systems with future geostationary satellites. But let's have a look at ground-based radiometers as we know them. So this is probably nothing new to you. So just a recap here. They have the possibility of excellently retrieving the integrated water vapor content of the whole troposphere. It's the best method to derive the integrated cloud water column with high accuracies around 10 grams per square meter, but they also have then in the V-band the possibility to accurately profile the temperature, at least in the atmospheric boundary layer. And here we're talking about accuracies of 0.5 to 1 Kelvin within the lowest 1 to 2 kilometers. So this is actually not new. So this is something that has been known for quite some time. But today we have now robust and accurate and affordable instruments which we can distribute in networks, 24/7 unmanned operations, continuously with resolutions from seconds to minutes. And there are emergent network structures which are delivering automated QA and QC brightness temperatures or retrieval products. And these network structures are also offering operator instructions centrally, which is very beneficial if you want to operate these types of systems within a quality-controlled network. But this all builds upon the legacy, right? So the first ground-based microwave, or the first microwave absorption measurements with a microwave radiometer, they go back to Dicke in the mid-40s, where we see here the publications, and the developments already, Dave Sterling in 1969 wrote a review about passive remote sensing at microwave wavelengths from the surface and also from space, noting that already in 1969, that passive remote sensing at microwave frequencies has applications which range from meteorology to oceanography and geology. and include measurements of temperature profile of the atmosphere and of the atmospheric distribution of water vapor and ozone. And such measurements can be made from space or from the ground. So that goes back quite some time. And that's how the instruments looked like, right? So Snyder in 1972 actually also stated that we can profile the temperature by using not only frequency dependencies in the V-band, but also elevation angle dependencies in the V-band, which we use today with our modern instruments, which look a little bit different than the ones in the past. But probably this one was also colorful, but it's just not in the picture. So, and then developments continued, and not really very fast, but of course, we have to mention Ed Westwater as one of the driving factors in ground-based microwave remote sensing in 2004. He, again, gave a review paper on surface-based microwave and millimeter wave radiometric remote sensing of the troposphere, together with Susanne Crevel and Christian Metzler, where he, amongst others, also mentioned that combining active and passive microwave remote sensing has very beneficial options for retrieving the atmospheric state. So passive, then, the case of cloud radar, but also the sense of profiling winds. Yeah, and at this point, I have to say, much of the work that my research group has been doing is built very much upon also the Hans Liebe fellows, which have talked here before me. So especially Dave Turner, which is sitting here, but also Susanne Crevel, Christian Metzler, and Nico Cimini also, who all of the work is very important for what we are doing in Cologne. So the rather slow but recent success story of ground-based radiometer networks starts maybe around something like 2000, mid-2000s, where then instruments were developed that are beginning to be network ready and to be deployed unmanned. And Nico Cimi and I, we founded the MWRnet, so a loose international network of ground-based radiometers, 2009, trying to pull together the different operators and the manufacturers towards harmonizing network structures. And then 2013, there's also now an article from Maria Cadadu, who was also a fellow here, and which then introduced the ARM radiometer network program and described how these liquid water path and integrated water sensors actually have been networked within the ARM program. And very recently, there's been the New York State Mesonet development, where you have 17 microwave radiometers and Doppler lidars within the state of New York, measuring these properties of winds, temperature, and humidity in the atmospheric boundary layer, idealized for improving numerical weather prediction. And then there are the predictions, or the projects in Europe, which I will shortly highlight, namely ACTRIS and UMETNet activities, which I show you here. These two networks are focusing on microwave radiometers, ceilometers, Doppler lidars, and in future also cloud radars. Concerning microwave radiometers, there's a network of about 30 to 40 instruments in Europe currently, and evolving in two networks. So one of them is ACTRIS, which I already mentioned, European Research Infrastructure Consortium for Aerosol Cloud and Trace Gas Observations, and there's a branch of ACTRIS related to cloud remote sensing. And within this, these microwave radiometers are networked. So there's research data available from these systems concerning clouds, thermodynamics, but also with Doppler wind lidars concerning wind profiling. And the idea is to make these data homogeneous and accessible to scientists all around the world. And on the other hand, we have the UMETNet program, which is collaboration of the different weather services in Europe, and they have an observations capability area called eProfile, which provides centrally data to the European weather services. And eProfile concentrates on profiling the atmosphere. And within this observations capability area, ceilometers have already been incorporated, so are real-time available for the weather services. And at the moment, microwave radiometers and Doppler lidars are being incorporated so that in a few years from now, these data will be operationally available to all the weather services within UMedNet. And just to show you some examples of what's going on in the Actris network, so in order to operate a research data network, research infrastructure, it's important to ensure network-wide quality standards on instrument setup, calibration, measurement configuration, maintenance, data processing, QA/QC, providing quick looks. And this is done within Actris, coordinated at the University of Cologne within my group. And there are then now software packages available specifically for microwave radiometer processing, so coming in here, the raw data which are being quality controlled, retrievals are applied, we have common NetCDF formats, some of the data are used then for synergy retrievals in other retrieval products, and they are visualized online, more or less in near real time, and through the cloudnet.fmi site, you can actually view all of the instruments which are currently contributing to the network. So these are then centrally processed retrievals of water vapor and temperature profiles, as well as also the level 1 brightness temperature data. So that's concerning the network structures, and just a short review on actually how does this work with the ground-based microwave radiometer profiling. We measure in 2 bands, in the K band here around the 22.235 gigahertz water vapor absorption line, and in the left-hand side of the 60 gigahertz oxygen absorption complex. With the K band measurements, we have typically 7 measurements on the right shoulder of the absorption line. And the pressure, so we have here an optically thin feature, and that means that through the pressure broadened water vapor feature, we can actually get some information on the vertical structure of the water vapor. So going from the line center to the shoulder, we see here the weighting functions, and we see how the information content at the line center increases with height, and at the shoulder decreases with height. So this is due to the pressure broadening of the optical thin feature, which we can use then to profile water vapor. On the other hand, we have the optical thick oxygen absorption complex at around 60 gigahertz, and we know that O2 is at a constant mixing ratio with height, and so the brightness temperatures we measure are only a function of temperature and pressure, so we can use this to derive the temperature profile, and we see that the more optically thick, the closer we are to the complex center, and this gives us information that the brightness temperatures measured here are much closer to my instruments than the brightness temperatures measured here, which represent then the column to a certain typical height. So disentangling these relationships allows us to profile the temperature, and not only additionally using this frequency-dependent brightness temperature information, but also from elevation scanning, because we use again the fact that here we have an optically thick atmosphere, and that then observations from lower elevation angles then stem mainly from low heights as well. And combining elevation and frequency-dependent brightness temperature measurements then give us the possibility to retrieve the temperature profile, and the better in the boundary layer than in the rest of the troposphere. But in order to actually retrieve temperature and humidity profiles, we need to be able to forward model these, and we need to be able to simulate the brightness temperatures. And typically this is done from space using RT-TOF. Maybe one or other of you have heard about this very fast rate of transfer model developed within UMedSat numerical weather prediction satellite application facility. It's widely used in the NWP community and simulates specific satellite instruments, radiance, brightness temperatures, and the Jacobians from model output. And within the microwave radiometer community led by Nico Cimini, RT-TOF ground-based has been developed. It's a corresponding fast RT model for upward-looking microwave radiometers. You can find this in De Angelis et al. 2016. It was developed within this MWRnet initiative, and now this computes brightness, temperatures, and Jacobians for most ground-based microwave radiometers which are currently in use. And this builds upon the groundbreaking work of Hans Liebe's millimeter wave propagation model, which was finalized in 1990. So these fast models, they're basically parametrizing the line-by-line calculation, but the line-by-line calculation is based on Hans Liebe's millimeter wave propagation model, and also by the line-by-line microwave radiative transfer model by Phil Rosenkrantz, which is documented here in 2017. But these models are essential for doing any types of retrievals, for doing any of the work that we are currently doing in the temperature, water vapor, and liquid water retrieval application. Yeah, so I highlighted some of the potential here. Now the limitations of ground-based microwave radiometers. This is a typical error uncertainty, which you see here, right? So we have here the temperature differences between a microwave radiometer and a sonde, a statistic. We have here the systematic error in black, and the uncertainty here on the right-hand side, so the bold one here. And we do see that there can be some issues leading to systematic uncertainties of temperature in the lowest part of the troposphere, which can be due to instrument drifts or calibration uncertainties. And this can often lead to required offset corrections in the retrieved profiles, which, if you know the bias is constant, you can actually correct these out here, for example. And but of course, these bias errors can also be due to external sources such as wet radome, so water on the radome of the instrument scattering due to precipitation, which is happening above, which is not encountered in these fast radiative transfer models, or radio frequency interference, which is becoming more and more important. But if you look at the uncertainty here, then this is mostly not due to such error sources, but is inherent in the physics of the problem. Right? So this increase in uncertainty with height, actually, we can also convert into degrees of freedom for signal. So this is something I can ask myself, how many independent levels of temperature and water vapor can I retrieve, right? So, and from a variational retrieval, I can retrieve a matrix called the averaging kernel. If I take the trace of this averaging kernel, I can exactly answer this question. And this is due to really the microwave radiative transfer, which limits the physics or the accuracy of these retrievals. And temperature retrievals, they show degrees of freedom of signal for 3 to 4. And most of this information is contained in the boundary layer. So down here where we have also high accuracies. And above we then have a strongly smooth profile of the temperature profile. And yeah, the humidity profile has a degree of 2 only, freedom for signal. And this means that we basically have a strongly smooth profile throughout the whole troposphere. But in spite of these deficiencies or limitations, microwave radiometers from the ground have been used in data assimilation approaches and have shown to have a positive impact as well. So back in 2016, in a collaboration with some French colleagues, we had a first network of microwave radiometers that showed actually a nice impact on significant precipitation in the Mediterranean, on forecasting this in the Mediterranean region. And just a few weeks ago, an article was published from some colleagues from DWD and Meteo Swiss that showed how the impacts of 2 currently operationally operating microwave radiometers at Meteo Swiss are changing the initial state of the model. And also there have been sensitivity experiments with different channel combinations at DWD to see how really these systems can then improve numerical short-term predictions. You can also test this with OSSI, so observation system simulation experiments. So this is the case where you have a completely simulated environment. You have a nature run that is your truth. You forward model your brightness temperatures, and this way you can have arbitrary configurations of measurements in your domain. And this is what was done by Maria Toporov in my group. So she's taken the URSI framework of the DWD, and she's planted 218 microwave radiometers into the region of the ICON model over Central Europe, and has for 1 or 2 days tried to specify the impact of these systems. And what you see here are uncertainties of the forecast without any assimilation, uncertainties of the forecast as a function of height in temperature, with microwave and conventional observations, and only conventional observations. And here's the forecast impacts for 1 hour. And here's the improvements on the initial state, so on the analysis. And you see that for the temperature, you have positive impacts of this microwave radiometer in the lowest kilometer, as we could expect from the retrieval uncertainties. So this is really also impacting not only the initial state of the model, but also improving the forecasts of temperature in the first few hours. And this is also the case for humidity, where you actually see that you have positive microwave radiometer impacts throughout the lower troposphere up to almost 4 kilometers, and where the assimilation of microwave plus the conventional observations during the 1 hour forecast is here really very beneficial if you would have these 218 systems in your measurement network, which is of course not the case, though this is purely hypothetical. Okay, so that's what microwave radiometers are capable of doing on their own. Right? But can they be better if they are combined with other systems? Right? So you could combine them with other types of ground-based remote sensing instruments. Here's a sketch from Wolfmeyer et al., which I adapted a little bit. So lots of other remote sensing instruments from the ground which can improve water vapor and temperature retrievals. For example, Raman LiDAR or differential absorption LiDAR, they really have a high temporal and vertical resolution concerning water vapor. But they do have limitations as well, so incomplete overlap in the ABL, so you can only start interpreting the measurements after a few hundred meters. Clouds attenuate the signal, and they are hardly network ready yet. And there's also the infrared spectrometer, so you have the AIRS or YASI sensors from the surface looking upward. You can get 2 to 3 times more degrees of freedom for signal, for temperature and humidity profiling compared to microwave radiometers. But again, clouds saturate the signal, so this is valid only during clear sky cases. And the data changing processing is very challenging and is also not standardized yet. So yeah, microwave radiometers are the ones that are the most sophisticated in this sense at the moment. Of course, there are other possibilities to better the thermodynamic profiling, so meteorological drones or radioacoustic sounding system and other instruments, which I'm mentioning here to be complete. But if you look at a synergy of microwave radiometer and water vapor LiDAR, here's an example of some work that I've done together with Dave Turner, and here's a modified sketch or looking at temperature uncertainty as a function of height. And here you see the red bold line is using the microwave radiometer only. And if we combine a water vapor dial, so this water vapor LiDAR measurement where you can see here, this is the measurement range of this system, okay? And if you combine, so this is the uncertainty statistic you get from these 2 degrees of freedom signals, 2 degrees of signal, 2 degrees of freedom for signal, compared to if you combine it in a variational retrieval with a water vapor dial, right? So what you see that the microwave radiometer is essential for the retrieval in the lowest layers in this combination, and in the upper middle troposphere, significant improvement you can then actually obtain through the passive and active synergy of these systems. And if you look at the temperature retrievals, although this is only a water vapor retrieval system, the water vapor dial in the variational retrieval actually improves also the microwave temperature retrieval a bit due to the temperature and water vapor correlations which we can actually consider in this variational retrieval. So that's an example how these two systems can work together, and also highly spectrally infrared resolving instruments can also lead to similar improvements, and especially if you bring all three or even more systems together. But what about combining satellites with these ground-based systems? Because satellite information, if you have a geostationary one, is available all the time. If the satellite is looking at your instrument location. So the questions we can ask is, how does the accuracy of temperature and humidity profile retrievals improve if microwave radiometers are located at the subsatellite point? What is the influence of microwave point measurements within a 2D field of satellite observations, for example, of atmospheric stability, which is very closely related to the temperature and humidity? So one satellite that's upcoming is the Meteosat third generation sounding mission, MTGS. So it has a hyperspectral infrared sounder on board, and it's something that will be able to deliver a three-dimensional weather cube over Central Europe concerning water vapor, temperature, ozone, every 30 minutes with a footprint of about 6 by 6 kilometers. And the launch is planned for the third quarter of 2024. And the question is, can this satellite actually revolutionize weather observations? Because next to the 2 times daily passes of the polar orbiters, we now have these observations available every 30 minutes. And so here are some of the spectral regions. So from the CO2 spectral region, we can derive temperature profiles, water vapor profiles. So both of them are achievable. And if you look at the sketch here, so here's the satellite looking at an atmospheric column. Here are the weighting functions of these high number of channels. You can see that most of these channels deliver information in the middle and in the upper troposphere. But if you now combine this with the ground-based radiometer, which is looking at the same column from downward towards the satellite, and you look at the weighting functions here, you can see that they are mostly concentrated in the atmospheric boundary layer. So we actually have complementary temperature weighting functions, which should, if used together, provide a much better picture of the atmospheric state. So what we do, we develop a retrieval for both of these systems together. So we use temperature and water vapor profiles we use from a hypothetical satellite and ground-based observation network. Right? We don't have these satellite measurements yet, and we don't have these networks of ground-based remote sensing systems, so we do everything in a hypothetical environment. We use reanalysis at a 2-kilometer resolution, so the COSMO reanalysis over here, the central part of Europe. We simulate the IRS and the microwave radiometer observations with RTTOF and RTTOF ground-based, and then we relate the simulated observations to the atmospheric stability or to the temperature and humidity profiling from the reanalysis via neural network retrievals. And then we can use actually the truth so apply these neural network retrievals then from the simulated brightness temperatures to the output of the reanalysis, and then obtain the uncertainty estimates of these retrievals. And these are the ones that I would like to show you now. So here are uncertainty information plots about the satellite retrieval only is the blue one, the microwave radiometer only retrieval is the yellow line, the combination of the two is the red line. And this is for temperature. And you see here the temperature uncertainties as a function of height for clear sky and for cloudy sky. And you see that the ground-based microwave radiometer is significantly better in the atmospheric boundary layer lower troposphere, especially in cloudy cases. So this is the green line here compared to the blue line of the satellite. Satellite is, of course, not able to see below the cloud cover because it's the cloud is always close to a black body emitter, and in the infrared. So here the microwave radiometer dominates. But we do also see here in clear sky cases that this level is a little bit lower. And in some cases, the red line is better than the blue or the yellow line. And this is the region of the synergy benefit, actually, right? So the synergy benefit is where not only one single observation type dominates, but where the combination of both observations actually lead to a combined improvement. So for the temperature profile retrieval, this is somewhere around 2 kilometers in the boundary layer you see here. And in the cloudy case, there's a synergy benefit all the way up throughout the troposphere. Yeah, and what you can else see is this black curve here is instead of using a microwave radiometer at the surface, we use just typical synop observations of temperature and humidity. And you see that this also leads to improvement already with respect to the satellite uncertainty, but using the profiling instrument from the microwave radiometer is still quite better than using only the surface sensors combined. You can do this also for the humidity retrieval, right? You see, again, the ground-based retrievals with better performance in the atmospheric boundary layer, especially in the troposphere and especially in cloudy cases here, right? This is here the red and the green line. But you see here, of course, specifically in this clear sky, that the satellite retrieval is better than the microwave retrieval from the surface in the upper parts of the troposphere, middle and upper parts of the troposphere. But adding a ground-based microwave radiometer to this future satellite can lead to an uncertainty reduction of up to 100% in absolute humidity, right? Especially in the boundary layer, which you see here, which is, I think, quite a statement. And the actual synergy benefit, so the differences between the red line and the blue or the yellow line is valid throughout the whole troposphere, basically. So this means that synergy of the instruments is always having an impact, right? So combining surface and ground-based sensors, surface and satellite sensors. So that's when both instruments are looking at the same column, but what happens when you want to characterize the representativeness of one of these point measurements, because we don't have microwave radiometers at every satellite pixel available, right? So what is the benefit of adding 1, 2, or 3, or 4, or even more microwave radiometers in a certain domain to the satellite retrieval? And we have looked at this, again, this is work from my postdoc Maria Toporov in the 2D stability index field. So we used the lifted index, which is an index for stability. We looked at a very specific region over Germany, the Rhine-Ruhr area, which is pretty densely populated, one of the most densely populated areas in Europe. And Cologne, we are located here in the southern part of this Rhine-Ruhr area. So we, from the reanalysis, we calculated this lifted index, which is the temperature at 500 hectopascal minus the temperature of lifting air parcel dry adiabatically to 500 hectopascal. And if you have this number, if it's smaller than 1 degree Celsius, you have a chance for thunderstorms, and you have typical values are from -10 to +15, where -10 indicate very unstable, so a very strongly convective cases or potentially convective cases, and +15 means very stable cases. So now what happens if we have the future satellite configuration measuring this IRS system, and what happens if we add 1 microwave radiometer, 5, 9, or up to 41 to the lifted index retrievals from the infrared sounder system. And okay, the maximum possible would be in our configuration of the Rhine-Ruhr area would be 1,521 microwave radiometers, but I don't know anybody who would be able to maintain these and buy these, actually. So that would be the maximum possible, but we're looking now at realistic scenarios, and give you some background on the math here, how we did that. So XA is the updated, lifted index synergy field at every satellite pixel, so at all of these 521 points. using the background. The background is the retrieval from the satellite at every satellite pixel, but then we have the observations here, and the observations in our case are the lifted index retrieved from satellite and microwave radiometer synergy at each microwave radiometer location, so at these red points here. So this is exactly where we're doing the synergy I was just describing a few slides before. And then we can calculate this gain matrix for the synergy observations, which uses the information in the correlation of the background error covariance of the IRS retrieval and the correlation in the observation area, error in the observation array. And this is then the microwave and infrared sounder retrieval. So using these error correlations then spread the information of one microwave radiometer system to the other satellite pixels. So we get an updated XA then at every satellite pixel. And to show you some of the results, so we have 3 lifted index scenes here for summer season at 3 different times. And here are the black dots. They are actually indicating the 10 hypothetical microwave radiometer locations. Currently, these are ceilometer locations, which could be realistically equipped with a microwave radiometer. And we have here the truth of the lifted index. So this is from the reanalysis, where we calculate the stability index. And then we can apply the satellite-only retrieval, right? So here we have a clear sky case. So here the liquid water path, which is shown in the bluish color, is 0, basically everywhere. So here the IRS retrieval and the IRS plus the 10 microwave radiometers distributed at these points here, they look, not very different and are more or less very similar to the truth. But this is the clear sky case. So what happens in the temporal evolution when clouds appear and when the stability actually is decreasing, so the instability is increasing, then we see that the IRS has these massive problems in detecting these stability changes because the clouds are simply blocking the signal. And if we take these 10 microwave radiometers, in addition, we can see that this ground-based network can then significantly improve these IRS observations to come more or less close to the original reanalysis stability field. We can do this not only for these 10 hypothetical stations, but increase the number of microwave profilers to ask us the questions, how many of these microwave radiometers should we optimally deploy in this region? So far, we had these 10 locations, but what we did now then was to distribute up to 200 microwave radiometers equidistantly, and we show you statistics for summer months of 2 years, and they look like this here. So here's the root mean square error of this lifted index as a function of the number of microwave radiometers. And the red curves are the ones corresponding to the slide just before, so using the synergy retrieval to update the satellite-only retrieval. And you see here the blue point here, so up here is the cloudy satellite retrieval, up here is the clear sky satellite retrieval. So what happens then when we, in the clear sky, then add up to 200 microwave radiometers in the RMSE we see here. And we have, still a very visible improvement here, but the best improvement is, of course, in the cloudy case, which is here the dashed line where we see very significant improvements which correspond to a couple of tens of microwave radiometers located in this situation. The green lines are indicating the case where we don't use the synergy retrieval, but only the retrieval of the microwave radiometer and combine that with the infrared retrieval background field. But you see the red lines make clear, because the red lines are in both cases much better than the green lines, that the synergy retrieval is very, very important for adding information content. Yeah, and if you look at this by eye, you could say, okay, something like 35 microwave radiometers distributed over the Rhine-Ruhr area in combination with a future infrared sounding satellite would be some kind of optimal configuration to really improve the stability observations that are needed for nowcasting of thunderstorms, for example. Yeah, and if you can spread this information to Germany, and that would mean something like 300 microwave radiometers over Germany. Okay, that's not for us to decide, that's for us to say that this could have a positive impact. But in order to get this positive impact, you need to really increase the number of ground-based sensors to a certain extent. Yeah. I hope I convinced you that would be important, and come to my summary. So, stating that the potential of microwave radiometers for thermodynamic profiling has been known for over 70 years, but nowadays we are at the stage where where technology exists that they are finally ready for network and for operational applications, so you can really put those sensors out there and let them run unmanned 24/7. How to do this is being implemented currently in the first networks I presented in the Actress and the UMIDNet e-profile networks. So this is what's happening in Europe currently. I tried to convince you that there are now data assimilation trials available, and that their first impacts show that microwave radiometers alone can have already a significant impact on the analysis and on the short-term forecast with respect to temperature and humidity. And that microwave radiometers do have limitations concerning their vertical resolution, inherently due to the physics of absorption, but the synergy with satellite sensors, I think, shows high benefits for the numerical weather prediction applications. And so the challenges, I think, in the next 1 to 2 decades will be to answer the question, is it worth to establish and operate ground-based microwave radiometer networks with a sufficient number of sensors? And actually, we need more impact studies to know where we have areas to expect this high impact of the ground-based remote sensing systems. And I think we are only at the beginning of quantifying this, but if we want to push towards networks of these systems with a much higher density than is currently planned, we have to have quantitative arguments, and I think this is the main challenge for the next few years. And with that, I'd like to thank you for your attention, and I'm happy to take any questions.
Thank you very much, Professor Lohnert. Very illuminating talk. And we have time for questions, so please.
Yeah, so the question was if we use our own retrieval algorithms within this Actress network. We use statistical retrievals which are based upon ERA 5 output, and we try to use the reanalysis to homogenize the retrieval approach over the network. So we have, this belongs to the quality assurance procedure, that not everybody uses his or her own retrieval, where we, in the end, can't judge how they were created. So this processing will be done in future centrally at the Actress Data Hub. Something similar is done in eProfile, but this will be based on a variational retrieval scheme. Yes. The question was if we have seen differences between the manufacturer-supplied retrieval and between the ones we develop. Yes, we have seen very significant differences. And it's very difficult to judge where these differences are coming from, which requires, getting very closely in touch with the manufacturers. But yeah, soon we have different manufacturers, we have different approaches, but the bottom line is that we need homogenized retrievals for the whole network, and this is why it will be done both in Actress and in eProfile centrally from the level 1 brightness temperatures we receive.
Jessie?
You discussed the lifting index, and I was wondering, how could you synthesize the data that you get from that to determine, like, if in a certain geographical location, or if you're experiencing something like wind shear, how could you, like, synthesize that to severe technical development in the area?
I'm not sure if I completely understood. Maybe, yeah.
So just like with the lift index data that you
The lifted index, yeah. Mhm.
I was wondering if you were able to synthesize that data to certain geographical locations, or if you're
Ah.
developing like wind shear or something. How could you synthesize that to determine severe development?
Well, yeah, well, lifted index is just one stability index, which is used among others, right? There are much more complex ones that include the dynamics and the wind shear. But yeah, this was a first approach to use the easiest stability index to see what we can get on concerning results with respect to, of course, concerning topography, and there are many other factors that come into play. But we showed here statistics, right? The lines I showed at the end were statistics over 2 years of summer months. So at least with respect to LE over this region, I think it's statistically significant. But if you believe LE or not to be a thunderstorm or a strong storm indicator, that's of course another issue. But yeah, it's
You have a question, Dave?
So I'll broadcast for others. This works too. When you assimilate the cloud, either the temperature and water vapor profiles into the NWP model, one of the challenges that we have with NWP models, climate models, everything is just clouds in general. Do you see any improvement in the clouds by assimilating the thermodynamic profiles?
We didn't assimilate the profiles, but the brightness temperatures, if you're referring to the USSI experiment.
But it should be the same information.
Yeah, it should be the
so
same.
does it improve the
Yeah.
clouds?
We did this just at the very beginning, so these are very first results, and I think at the moment it was clear sky, which we looked at, but yeah, further step would be to look and hope the clouds will also be affected. But that's, yeah.
Thank you. Any other questions? I have one question. What is the difference between RTTOV and RTTOV-GB? What did you change in the ground-based version of RTTOV to make it more relevant?
Well, we needed to change the complete geometry, right? So I think,
Geometry.
yeah.
Yeah. Mm-hmm.
So it's
Uplooking versus downlooking.
transmittance-based, right? We need to parameterize the transmittance. And it's parameterized as a function of temperature, pressure, and water vapor. So it's much, and then of course we also need to consider the different characteristics, the bandwidths and of the instruments.
Right,
Right?
exactly.
So it's very instrument specific.
Yeah, thank you. Any other questions? Just a minute, let me get you the microphone.
I'm not as familiar with frequency allocations in Europe, but I know that here in America there are concerns about 5G interfering with weather radiometers. Is there a concern about being able to deploy this many radiometers and not have interference?
Yes. Yes, there is a lot of concern. At the moment in Europe, the frequencies are not in that high gigahertz range, so we're starting around 20 gigahertz, and the 22 line is certainly protected. But what will happen in future, there's a big question mark, of course, and yeah. But I think making aware, also I think conferences like these, that these bands need to be protected every time, and every time repeating this again and again, I think, is very important. Yeah.
Thank you.
Fred.
What about GPS technologies?
For water vapor, yeah. This is, I think, something that is available at many, many places, I think over the US and over Europe, and where we get these approximations of the integrated water vapor, right, from different satellite configurations that, and I think the accuracies are maybe not as good as from the microwave radiometer, but certainly within the same order of magnitude. So I think they are already, if I'm not mistaken, or have been test-wise assimilated at the German Weather Service as well. So yeah, definitely important.
I have one last question, if I can, and that is, if you could reduce the bias and delta TRMS on each of the radiometers you use in the network, would that have significant impact on the results you're finding?
Like we just talked a few minutes ago, yeah. I think the bias is the most important problem. So getting rid of the systematic errors,
Yeah.
I think that's the problem that is dominating everything.
Yeah.
And if we get the radiometric noise better, I think there have been studies that show that you can improve the temperature profile to a certain degree. But yeah, then the question is if you need that and how good you can get in theory. So going to, exploring the limits of where you can go is maybe then a sensitivity study you need to carry out.
And I realize we did just talk about that before the lecture, but I wanted to make sure for the radiometric engineers in the audience that they did hear that as well.
Okay.
So thank you for repeating that. Let's see, any last questions then? Okay, if not, I'd like to thank Professor Lohnert for
Thank
being
you.
our Hans Liebe Fellow this year and for this wonderful lecture. We appreciate it so much you're coming here.
Yes. Thank you for inviting me and giving the chance, and I'm very much honored to have been here and to have given this talk. And
Thank you, it's our pleasure.
thank you.